2019, working in the radio astronomy program of NRC Hertzberg at the DRAO. So currently she is a Banting and KIAC fellow at the Stanford University. So Dr. Tahani works on everything related to magnetic fields in the universe through observations, theories, and instrumentation. And she studies how galaxies evolve and how molecular clouds, star formation evolve by mapping interstellar magnetic fields. So today we're going to hear her talking about the role of magnetic fields in star formation, especially constructing 3D field configurations.
Thank you very much. Right, thank you very much. It's wonderful to be in Arizona. As Joe mentioned, my name is Mehrnoosh Tahani, and at Stanford University. And today I'd like to talk about the role of magnetic fields in star formation and first complete 3D magnetic field observations of molecular clouds. So first I'll give a brief introduction. And for this talk, I'm focusing on molecular clouds. So I'll briefly discuss molecular clouds. Then I'll talk about the novel techniques that we developed to reconstruct the complete 3D magnetic fields associated with molecular clouds. And then finally, I'll discuss the astrophysical insights that we can gain from these 3D observations. And one thing I like to emphasize is that when I say 3D, I mean real 3D. So in position space, including the vector direction. So in the past decade or so, recent observations have greatly enhanced our understanding of the structure of the galaxy, for example, by Gaia observations. We know that we are located in a local bubble, and this local bubble hosts a number of molecular clouds on the surface of itself or on the shell. And there's another bubble that is quite interesting, and we'll come back to it repeatedly through the talk, which is the per-tau bubble, which hosts a number of molecular clouds as well on the surface. For example, the Perseus molecular cloud, the Taurus molecular clouds, which are star-forming clouds, and as well as some nearby Orion clouds. The local bubble itself consists of many other molecular clouds, for example, the mysterious Moscow filament, Ophiuchus, Lopez, and so on. What we know about these molecular clouds is that they gravitationally collapse to form stars. And what we know is that the star formation actually happens inside filaments inside these molecular clouds. So there was a study by Andre 2010 that showed that all the star-forming cores that they identified lie within the filaments within molecular clouds. So these filaments, you may say, what's interesting about them? We see them every day, and the clouds in the sky, steam from a cup of coffee, cigarette smoke, and drop of ink in a glass of water. But what makes interstellar filaments unique is that we cannot explain their characteristics and their lifetime without including magnetic fields. So magnetic fields are playing very important roles in the formation of these filaments and their evolution, and for filaments within molecular clouds, and their evolution to formation of stars within these molecular clouds. So magnetic fields are playing very important but mysterious roles. We know that from very early on phases of star formation, which one can say as cloud formation, they can slow this process down. And as the cloud evolves to form stars, this process may be slowed down depending on the orientation of magnetic field with respect to molecular clouds. And sometimes we don't really know what roles they're playing. Are they helping star formation or are they hindering the star formation? But one thing that we know for sure is that they emerge as the hero of the star formation story at the end by slowing down the rapidly spinning star forming cores and allowing for the star formation to happen through magnetic braking. So to understand the roles that magnetic fields are playing in the evolution of the galaxy, formation of interstellar filaments, formation of molecular clouds, filaments, and stars, we need to observe them. And specifically, we need to observe their orientation with respect to these density structures. So these filaments I specifically mentioned in terms of molecular clouds within molecular clouds, but they are ubiquitous in the interstellar medium. We have diffuse atomic hydrogen filaments, we have filamentary molecular clouds, and we have filaments within molecular clouds. And we can look at the orientation of magnetic fields with respect to these filaments. When we look at the orientation of magnetic fields, when projected onto the plane of the sky with respect to diffuse filaments, we see that they're parallel to each other statistically. And when we look at the orientation of magnetic fields with respect to filaments that are denser, we see that statistically, they're perpendicular to each other. So if we summarize the past decade of observation, what we see, as we did in the Protostar and Planet 7 chapter with Kate Patel, Laura Fiesel, Leah Tia Liu, and Eva Tormosi, is that we see this statistic alignment through the star formation process. So when we look at the orientation of magnetic fields with respect to clouds, molecular clouds in general, we see that in general, magnetic fields are parallel to low density structures and perpendicular to high density structures. When we go to filaments within these molecular clouds, we see the same relation, parallel to low density structures and perpendicular to high density structures. In these scales of filaments, we see another transition back to parallel at very high density filaments. And that's what we think when gravity is taking over and pulling the magnetic fields with itself. I won't talk about the core scales today, but I've listed it there just in case. And these orientations of magnetic fields with respect to these filaments of the clouds or within molecular clouds have important implication for the star formation process. So if we have the filament and the magnetic field parallel to each other, it can resist the radial contraction or radial collapse of the filament, and vice versa. If we have magnetic fields perpendicular to filaments, it can resist the contraction along the main axis of the filament of fragmentation in this scenario. So this would result in different modes of fragmentation, as was studied by a number of work and papers, for example, Seifert et al. 2015. And this would result in different star formation rates, star formation efficiency, and possibly star formation stellar masses as well. So understanding the orientation of magnetic fields is very important for understanding the roles that they play in the star formation process. But we can also get information about the strength of magnetic field. So when we look at the energy distribution of magnetic field with respect to turbulence or gravity, in cloud scales, we see that magnetic fields are dominating the system. So the systems are subalphinic, meaning that they're stronger than turbulent energies, and they're subcritical, meaning that they're stronger than gravitational energies. When we go to filament scales within molecular clouds, we see that starts to change. The system can be sub or trans or super alphanic or critical, meaning that we can have gravity, turbulence, or magnetic field dominating the systems. I've listed the core scale again here, but I won't talk about them here. And oh yeah, and one thing I forgot to mention, if you have any questions, please feel free to interrupt at any time. So one thing about the energy distributions that I like to highlight is that these observations are statistic, and they're mostly using a technique known as Davis-Chandrasekhar-Fermi technique, which can overestimate magnetic fields. So this means that the systems that we think are sub-alphanic, subcritical, and magnetic fields are dominating the system may be actually trans or super alphanic or critical. But the good news is that we can actually gain a lot of information about the geometry of magnetic fields and orientation of magnetic fields with respect to density structures, and particularly about the geometry of 3D magnetic fields. And we care about 3D magnetic fields because if we have a cloud, as we can see in the gray scale here, if I show with my cursor here, if we have a molecular cloud and a magnetic field that are perpendicular to each other, we have a line of sight component and a plane of sky component. So when projected onto the plane of the sky, as you can see here, they can look parallel to each other, but in reality, they're perpendicular to each other. So to understand the role that magnetic fields are playing in the formation of clouds, evolution, and formation of stars, we need to observe them in 3D. So hopefully I've convinced you that we need to observe magnetic fields in 3D, and magnetic fields are cool and important. So now let's talk about the techniques that we developed to observe magnetic fields in 3D. And first, let's start by common techniques of observing magnetic fields. So there are multi-ways or different ways to observe magnetic fields across the spectrum. And we actually need multi-wavelength observations to reconstruct the 3D magnetic field. So let's start by far infrared observations. So dust polarization is a technique that has been used to determine the plane of sky component of magnetic fields, and it has been widely used, and it's based on the alignment of interstellar dust grains perpendicular to magnetic fields. And a number of observations on telescope by, for example, Planck, James Clerk Maxwell Telescope, SOFIA have made these observations of galaxy and molecular clouds specifically. So here I'm showing the Planck results. The density structure is shown by the color coding, and the curved or drapery lines show the plane of sky magnetic fields observed by Planck. And to improve resolution compared to Planck, we actually made observations of a number of molecular clouds and star-forming regions with the James Clerk Maxwell Telescope. So here I'm showing the NGC 6334, which is a massive star-forming region in the disk of the galaxy. And so the grayscale shows the background color, and the orange lines show the plane of sky magnetic fields projected onto the plane of the sky. And what's interesting in this cloud is that with Planck, when we look, we actually see, yes, the large-scale magnetic fields are perpendicular to this structure. But when we zoom in with JCMT, we see a lot of structures that we were not able to see before. And these structures are telling us about the star formation processes that are happening inside this cloud. For example, this cloud is covered in a number of H2 regions formed by massive stars. One of them I'm showing here. And what we see is that these H2 regions can push the magnetic fields and orient them tangential to the surface of the bubbles that are formed. And in this study, we've characterized this alignment, but I won't talk about that in detail here. When we look at the regions that are very massive and are forming stars and cores actively, we see that magnetic fields are actually oriented by gravity. And even though in these regions we have H2 regions, are not energetic enough compared to gravity to push the field lines and orient them tangential to the surface of the bubble. So in this region, gravity is winning the game. And we can see across this cloud that there are a number of processes that are either influenced by magnetic fields, gravity, or H2 regions, and that's possible to know by observing magnetic fields. But these observations only give us the plane of sky magnetic field and averaged along the line of sight. So we need the line of sight magnetic field information, and we also need tomographic information so we can get rid of that averaging effects. For tomographic information, we can use near-infrared or optical observations and use, again, dust polarization, but instead, we look at the background stars. So we call this a starlight polarization. And because we know the distances to these stars, we can actually get a tomographic information about the plane of sky magnetic fields of these clouds. So in this cartoon, we can actually see that, okay, the cloud that is foreground to this star has this orientation of plane of sky magnetic field, and the other has another orientation of plane of sky magnetic field. So we can use this to find the components of magnetic field along the line of sight, for example, studied by Doi et al. 2021, which we found 2 components for the Perseus molecular cloud. Then we need Zeeman observations. For Zeeman observations, they're actually the most accurate technique to provide the strength of magnetic field. But they require strong magnetic fields and long telescope integration time, so there are not enough Zeeman observations associated with molecular clouds or diffuse regions available. So we need another line of sight technique while we developed our telescopes further and further, and that's Faraday rotation. So Faraday rotation provides the line of sight component of magnetic field and is the rotation of a linearly polarized electromagnetic wave in a magneto-ionic medium. And the amount of rotation is given by this formula, where lambda is the wavelength of the electromagnetic wave, and E is the electron volume density, B is magnetic field in the region, and L is the path length. And the quantity in parentheses is known as rotation measure. So if we have information about rotation measure, we can actually get information about magnetic fields. So now there are 3 main techniques that can use Faraday rotation to infer information about magnetic fields. So one technique is the classical technique that provides us with galactic magnetic fields or magnetic fields of highly ionized regions. And this has been widely used to tell us information about the magnetic field of our own galaxy specifically. Then we have Faraday tomography, which decomposes polarized intensity into components of rotation measure along the line of sight. In that case, we call them as Faraday depth. And this method can give us the magnetic field associated with different environments. And for molecular clouds, we have the technique that they developed in 2018 to get the line of sight magnetic fields associated with molecular clouds. So we're going to talk about this technique briefly. I won't talk about the details very much, but I'm happy to answer any questions you may have. So in this technique, the third one that I mentioned for molecular cloud, we use point sources, and these are extragalactic sources or pulsars that produce linearly polarized electromagnetic waves. And the region that is a magnetoionic medium is everything from between us and the point source that we have. And luckily, we have a number of rotation measure catalogs, or we can make observations to obtain rotation measure when we observe polarization angle at different wavelengths. So now that we have rotation measure of these point sources, to find the line of sight magnetic fields associated with molecular clouds, we had to answer two questions. The first question was, how do we find the rotation measure associated with the molecular cloud itself? And the second question, after we find the rotation measure of the cloud, is that, okay, in the formula, we needed electron volume density and path length. How do we find the electron volume density and path length? So we answered the first question using an on-off approach. So we take a number of points that are extragalactic points that fall near the cloud, but are far enough away from it that they're not probing the magnetic fields of the cloud. And we take on points. These are points that are on the cloud, or very near to the cloud, that are probing the magnetic fields of the cloud or associated with high density structures in these regions. Then to find the electron volume density and the path length, we use, so what I do is actually I assume that roughly the average line of sight magnetic field is constant, which is a reasonable assumption given all the assumptions and the techniques that are already available. And we take it out of the integral, and what we are left with is electron column density. So to find electron column density, we use extinction maps or column density maps. I specifically use column density maps by Herschel's, or extinction maps provided by Kainulainen et al. 2009, and a chemical evolution code developed by René Plum. Any chemical evolution code can be used, but this is what I've included here. And with this, we can find the electron volume density, and as the result, find the strength of magnetic field. So this has two components. First, finding the direction of line of sight magnetic fields, and that's just by using on and off points, and then finding the strength of magnetic fields by using chemical codes and extinction maps. So I'm happy to answer any questions about the technique itself, but let's get to the results. So what we found was that whenever we have nearby molecular Zeeman observations, our results are consistent in strength and in direction with the Zeeman observations. Compared with atomic Zeeman observations, they're consistent with the direction of atomic Zeeman observations. And another interesting thing that we find is shown in this figure. So here I'm showing the California molecular cloud. Circles show magnetic fields, line of sight magnetic fields. Blue shows magnetic field pointing toward you, and red shows magnetic field pointing away from you. And when we look carefully, we see that at one side, magnetic fields are predominantly pointing toward us, and at the other, they're predominantly pointing away from us. And this magnetic field reversal across the filamentary molecular cloud, we see it also in Orion A and in Perseus clouds. In the Orion A, this was previously observed with the same orientation using atomic Zeeman observation, and investigated in some theoretical studies proposing something like helical magnetic field morphology. So we actually have developed software and CB-LOS that can carry out this technique in an automated manner with the help of excellent students, John McNaught, Jennifer Glover, Ryan Claremont, and Gabriel Mono-Sarazua. The code is available on GitHub, and the software is available, and we would like more research groups and communities to use and provide us with feedback so we can further improve this software. So the software has multiple components. Two main components is an initialize component that first it installs everything that may be needed, for example, NumPy, AstroPy, Scalar, and so on. And it makes config files that are as the initial input parameters. And it also downloads all the data that are needed. So the rotation measure catalogs that are already available, and cloud maps by Herschel, and some extinction maps. Then we can, when we run the software, it makes the cloud directory, maps the rotation measure, finds B loss, the line of sight magnetic field, direction, and strength. And it actually generates a number of plots that the user can use to analyze, particularly the on-off measure to figure out if this on-off approach and the selection of off points is good. And this can be actually done on many molecular clouds with one single run using this command that I've listed here. So we've tried to keep the user manual short. It's only 7 pages, so short but descriptive, and the paper is also on archive as well. So now with this, we have the line of sight magnetic fields of molecular clouds. Let's see how we can take a step forward to get the plane of sky magnetic fields. So here I'm showing the Orion A molecular clouds. To get the 3D magnetic fields, I use Planck plane of sky magnetic fields shown by the drapery lines here, and constructed models that could explain this reversal, notably the arc-shaped magnetic field morphology that we will get into, or helical or toroidal magnetic field morphologies. And we used our plane of sky magnetic fields, Planck plane of sky magnetic field maps, and our line of sight magnetic field observations. We obtained synthetic observations from these models and compared them with real observations. And through a series of Monte Carlo analysis, investigating a range of systematic biases and chi-squared probability value, we concluded that an arc-shaped magnetic field morphology, where the magnetic fields bend around the filamentary structure and continue to the rest of the galaxy and the galactic magnetic fields, is the most probable candidate to explain this reversal that we're seeing. So in the arc-shaped magnetic field morphology, or in the Orion A cloud specifically, regardless of how the filamentary structure is formed, the environment is thought to be responsible, to be interacting with the field lines and bending them around the filamentary structure. But this arc shape so far, we only know it's arc. We don't know whether it's concave or convex from our point of view, and we don't have the plane of sky direction. So what we did next was we used galactic magnetic field models, particularly Jensen and Ferrer 2012, and plane of sky magnetic field observations, and line of sight magnetic field observations. And with these three, we were able to reconstruct the complete 3D magnetic field morphology associated with these molecular clouds. And here, I'm showing the Perseus molecular cloud, which also shows a reversal of magnetic field across the filamentary structure, and the line of sight and the plane of sky magnetic field observations. So with Jennifer Glover and Wednesday Lupikchu, we modeled the galactic magnetic field in this region, as we can see with the red vector, which when projected onto the plane of the sky, points in this direction. And it's actually, for the Perseus region, somewhat simple, because the Perseus cloud itself is somewhat parallel to the plane of sky, and the galactic magnetic field morphology that we modeled is also parallel. And using this, we reconstructed the 3D magnetic field, and this is the ordered magnetic field. So we are ignoring small-scale fluctuations and small-scale details in this region. And those ordered magnetic field can be shown here with the blue vectors, which continue to the rest of the galaxy here. So one thing I'll mention here is that in this region of the sky, although galactic magnetic field models may differ from each other, for their coherent component, which is the component that we are interested in because we want to look at how the magnetic fields were shaped, they agree with each other in the Perseus region and in the Orion region. So I showed Perseus. We also reconstructed the 3D magnetic field of Orion A. So this arc-shaped magnetic field morphology is also predicted in some cloud formation models. For example, cloud formation of Inutsuka et al. 2015, where a multi-compression is needed to form filamentary molecular clouds. So as the result, we would have a dense filamentary structure formed and a bent magnetic field, and the filament is formed as the location of this bending. So when we look at the velocity information and all the magnetic field information, we found it consistent with this cloud formation model. So we looked to see if we can explain this with observations. So if we have a dense cloud that is moving with the velocity v, and the magnetic field in the region has a component that is perpendicular to this region, and we have another shock front, which is by another bubble, then as a result, we have this bending of magnetic field morphology forming. So we used these magnetic field information that I already showed and velocity information, particularly C1 and H1 velocities, and found it consistent with these observations. So for CO velocity, so the dense blob that I showed in the previous slide, in the co-moving H1 frame, they're pointing away from us. So in this model, that would result in a concave magnetic field morphology for us, a magnetic field away from us at this point and toward us at this point, which is what we are seeing observationally and in the reconstruction of 3D fields. So because of this consistency, we look to see if there are any bubbles in this region. And in the first slide, or like second slide, I don't remember the number, we talked about the per tau bubble. So in this region, we do have a number of observations, including by Doi et al. 2021, Bialy et al. 2022, have identified the per tau bubble, which Perseus cloud is located behind from our point of view, and Taurus is located in the front of this shell. And what we know about this bubble, and for example, H2 bubbles that we saw early on, is that these bubbles can push magnetic fields and orient them tangential to the surface of the shell. We talked about it in terms of H2 regions initially, but this has been also observed by supernova remnant observations, for example, Focus and Brown 2008. So if, so we have the H2 region as well here. So if we assume that, okay, we have the initial magnetic field information, which is the coherent magnetic field orientation and direction that we get from our galactic magnetic field model, and we have the per tau bubble, So the per tau has pushed the magnetic field and has resulted in a tangential magnetic field morphology. Would this explain the observations? And the answer is no. This would not explain the observations because this bending is large and it may cancel out as average along the line of sight. We are seeing a sharp magnetic field reversal directly associated with the Perseus cloud. It's not large structure. And in the results that they showed, the uncertainty range was relatively large. So even with that uncertainty range, we were able to see this reversal. So should be something else. So because of that, I then proposed that there must be another structure behind the Perseus cloud. We don't know if it's a bubble or a sheet or what kind of a structure it is yet, that has interacted with the field lines and has further pushed the H1 gas and the magnetic field, resulting in a sharp arc-shaped magnetic field morphology directly associated with the Perseus cloud. So here, I'm showing the Perseus cloud with the orange bubble. I'll use the cursor again. With the orange bubble, and the per tau is shown with this bubble. And you can see a 3D cartoon of it here. So torus, Perseus, and per tau shell, and the structure, if it's a bubble, is shown with a green bubble or circle here. The cool thing is that right after I put this paper on arXiv, this presence of this structure was confirmed using kinematic observations. So this is telling us that with 3D magnetic fields, not only we can explain how these clouds and their magnetic fields were shaped and formed, we can also identify structures that were not visible with total intensity observations. So for the Perseus cloud, we are now able to explain its formation and identify structures that were not identified before. And one thing here, before I go to the next slide, is that you may tell me that, okay, Mehrnoosh, this is only 2 clouds that you've observed the 3D magnetic field structure, and the number of points are very limited. And I cannot agree with you more, so 100%. And that will change soon. So with the square kilometer array and its pathfinders and precursor, such as Meerkat or the Australian square kilometer array pathfinder, we will be able to observe a lot more rotation measure from extragalactic sources or pulsars. So for example, with current rotation measure catalogs that we have, we have 1 to 3 rotation measure per square degree. But with the POSSUM survey, for example, which is a survey using the Australian square kilometer array pathfinder, we will be able, or we are already making observations of a lot more rotation measures. So this will change to 25 rotation measure per square degree. And with the full scale, that would change to up to 1,000 points, rotation measure points per square degree. So this large structure, 3D magnetic field that I showed, we can actually not only see it for and observe the 3D magnetic fields for many more molecular clouds, we will be able to resolve details that we were not able to resolve before. And to keep up with these, we need better high resolution plane of sky magnetic field observations. And one of the observations that I'm passionate about is with the Fred Young submillimeter telescope, or CCAT prime. And we've already secured time to observe and reconstruct the 3D magnetic fields of a number of molecular clouds within the CCAT prime collaboration. And the galactic polarization group is actually led by Laura Fiesel as well. So now, with these 3D magnetic fields, let's put everything in a large structure or large perspective, big picture that we started with at the beginning of the talk. So to understand this 3D magnetic field geometry is in the large scale of local bubble. George Halal looked at the plane of sky magnetic fields in this region. And what we actually found was that the observed dust emission polarization or dust polarization fraction is highly influenced by complexities along the line of sight. So we do need these tomographic techniques. One tomographic technique that I mentioned was with optical observations or near infrared observations using starlight polarization. For example, with in Doi et al., we found two component magnetic field associated with the Perseus cloud. And we also have Faraday tomographic observations that we can observe. So Faraday tomography decomposes polarized intensity into components of rotation measure or Faraday depth along the line of sight. So if you look at the Perseus and the entire per tau bubble and look at this Faraday depth in this region, we will be able to put a comprehensive 3D tomographic view together. So we will be able to get detailed high-resolution 3D field across scales from galactic to prestellar core scales. And with that, I'll leave my summary slide, and I'm happy to take any questions you may have.
Questions in the audience? I have a question. Like, you have a for the model for the shock cloud. Have a spherical. You start with a spherical cloud. You plunge it into a kind of a sky field. How can you form a filament?
So formation of filament as a result of interaction with these bubbles. Is that what you're asking?
Yeah, the model, like you showed, you have a cloud, and you move it to a perpendicular magnetic field, you bend the field line, and I just wonder how does that give you a filament structure?
Great question. So there are ideal MHD simulations by Inu et al. 2018 where they looked at exactly this scenario. So a dense blob and a sheet-like structure of for example, H1 gas, and the blob moves toward the H1 or vice versa. And so what in the simulations, what is seen is that we can form magnetic fields also parallel to filaments parallel to magnetic fields, but the dense filamentary structure that in the simulation that is formed is perpendicular in the location of the bending of magnetic field morphology. And one thing I'd like to emphasize as well, this is one formation model that is consistent with two clouds that we found. We have to observe the 3D magnetic fields of many more molecular clouds to figure out the formation scenario for many more molecular clouds to see whether they are consistent with, for example, other formation mechanisms. So we discussed this a bit in the Protostar and Planet 7 chapter that we wrote.
And also, when you try to distinguish between whether it's a bending field or it's a helical field, because in my feeling is all you know is you have a reverse field along the filament structure, on the two sides of the filament structure. How can you know whether it's, say, in the back of the filament it goes this way and the front goes this way, or it's simply a bending? Because you don't know, you don't have the information in the back and the front of the filament.
Yeah, great question. It's not easy, so we could not fully rule out the helical magnetic field morphology. So when I constructed models and compared them with observations, what I found was that the arc-shaped magnetic field morphology is the most probable candidate to explain in these clouds.
By what confidence?
I don't remember the numbers off the
Yeah,
top of my head, but I can check and let you know. But then another thing that I've looked at is I use flash magnetic hydrodynamic simulation. So what I did was that I simulated an isothermal filament with a Palmer-like density profile. And I try to generate helical magnetic fields, even artificially by rotating the filament with very high rotation. And in none of the simulations, I could not generate a helical magnetic field morphology. But when I introduced with a student as well, velocity profiles to the filament, we could easily get arc-shaped magnetic field morphology. But this is a single isolated filament. And in the simulations in general, formation of helical fields are very, very difficult. But formation of arc-shaped fields happens often. So for example, I talked about Inoue et al. MHT simulations, or Lee et al. MHT simulations, Seifert et al. Also has simulations. So combining all these MHT simulations and the statistical analysis that we did, I'm confident, more confident for these two clouds, at least we're seeing arc-shaped magnetic field morphology. Thank you.
I guess how much you know about like the rotation aspects of these filaments and clouds, and are those aligned with the like if it was a helical magnetic aligned with the rotation of the observed filaments?
Yeah. So there were a number of studies to look at the velocity information to explain that this velocity information is as the result of rotation of the filament. So one of the studies was by Machida et al. 1990 something, and so we used the rotation that they had. I don't remember the number off the top of my head now in the simulation, but that did not work. I also talked with Alvaro Hacker, who has observed the velocity of these filaments over the years, and he said that he does not see evidence of the rotation of these filaments. So if there is helical fields, that cannot be explained through rotation. There is a possibility of non-ideal MHT simulations, because that's something people have not looked at to generate helical magnetic fields.
We have a question from online. Can we, Carlos, apologies if I missed the key point. Did I understand correctly that it's not the magnetic fields that shape the filaments, it's the filaments that shape the magnetic field?
Yes, great question. For these two clouds, yes, it's the environment, so the bubbles and interaction by multiple bubbles that are shaping the magnetic fields for these two clouds. I can't speak for all the observations, but for these two clouds, this perpendicular magnetic field morphology that we are seeing for these clouds are explained by arc-shaped magnetic field, which is as the result of interaction by environment and formation of clouds. But then it's a play, because then magnetic fields also, when we have the arc-shaped magnetic field morphology, like a valley, they allow for formation of or accumulation of more mass into the filament and formation of denser filaments. So I actually, even for these two clouds, I can't say confidently yes. The arc-shaped magnetic field morphology, we see that yes, is formed as the result of interaction with environments, but then the filament itself, we have accretion along the field lines into this arc valley into the filamentary structure. So it's a game.
So sorry, one more question on that. So in that case, initially, you have a cloud of gas that's able to bend the field.
Yeah.
That means in that case, your gas is dominating the field, right?
For the energetic super bubbles that we
because
have, yes.
If you have gas, if your gas can bend the field,
Yeah.
that must mean it's superzero velocity, right? It's the gas stop dominating the field. It can bend the field.
It can bend the field, but it cannot completely alter the shape of the field.
Yes, yes.
For example, if the alpha Mach number is 10, we would get completely perturbed magnetic field morphology.
Yes.
But with the alpha Mach number that we have, the magnetic fields retain a memory of the initial magnetic field morphology, but they get bent.
Yes, but in any case, a gas can bend the field.
Yes.
Then how can, basically it means gas can more or less really move through the field.
Yes. Yeah.
Then how can gas move in, follow the field?
How can get
Because if you have initial gas that can bend the field, basically gas dominating the field. But later, if you say your gas can flow in, accreting onto the filament, create the filament, following the field. But then you're saying basically gas can dominate the field and gas had to follow the field.
so the super bubbles that are generated. So for example, for per tau, this is estimated to be a number of 7 to 9 super bubbles over a lifetime. So they already result into the enhancement of the density structure into the surface of the bubble, and then the bending of magnetic field. And then after these, like when we have an initial filament formed, like a lower density filament, then we have accretion of matter, like gas and dust, into this valley of arc-shaped morphology. So in that scale, in that time scale, like after these expansion, after this bending, they're dominating the gas motion, and also with gravity as well, because there is an enhancement of the density structure.
Yeah, we talked about this.
Sure, yeah.
Another question online and Serena?
Yeah, I was also wondering if you have also took a look at the Orion B and found any connection between Orion A and B, and whether that could tell us about how filament formation in Orion might have happened.
I did look at Orion B. We have very limited rotation measure point for Orion B. So we only see one side of the line of filament because of one side of the filament. We don't see the other side. So once we have more data, we'll look at Orion B.
Yeah, another question is whether just in Orion A, which mode, the formation model that actually is a dominant way model for the filament formation in Orion A only, if you are, we're only thinking of the Orion A, because we know there are a couple of models, and then you mentioned about, I think, I'm not very familiar with that very well, but it seems like your 3D model can actually give an answer to give very good clue to how the formation happened.
Yeah, so for Orion A, the scale of the cloud that they looked at is a scale of 90 parsec. So if you look at the filaments within the Orion A, for example, the famous integral shape filament, then at that scale, I do not have enough data to talk about those scales yet. But for the large scale structure, we can see this. And it may be possible that for the smaller scale, so filaments of 1 to few parsecs, we may have helical magnetic field morphology for these scales. But for the scales that I talked about, 90 parsec, this is the arc-shaped magnetic field morphology consistent with expansion of bubbles. But for filaments within the Orion A, we need more data.
Yeah, thank you.
Thank you.
All right, let's thank our speaker again.